done mathematics, we've done physics. Let's start with the chemistry 2025 exams. This is level 1 chemistry. It's the sort of strange thing that they lump chemistry and biology together. But this is 92023, demonstrate understanding of how the physical properties of materials inform the use. It's a mouthful. It's just a general chemistry exam and introduction to chemistry. So once again, I'm just going to be using the version that's online, and I'm going to be using the formula paper that is provided, and I'm also going to be using the most common calculator, the Casio 9800. So with that said, let's do it to it. The first question begins with low density polyethylene, LDPE, is a type of polymer that can be used to make the body of a kayak. And the original exam paper had a picture of a kayak. I haven't included it because they cut it out on the online version. But they ask us to define a polymer. Well, let's look at the word itself. The word poly means many, as in Polynesia means many islands. So this is a bunch of monomers, which is one kind of molecule-ette that's been joined up lots and lots and lots of times. So this is a monomer, and then another monomer is attached to it, and another monomer is attached to it, and another monomer is attached to it, and another one, and another one, and another one, on and on and on and on and on, all joined up to make one massive molecule. And they're all bound together, so they're bound together really, really strongly. Bit of homework, if you want to see what an LDPE is, there's lots of examples of them in your house. If you just go to your bathroom, your toothpaste and probably your shampoo has got an LDPE, a symbol on it. It's a really, really common form of plastic. So now we're told that LDPE is widely used due to its versatility, moisture resistance, and low melting point. It is characterized by its low density and flexibility. A kayak needs to be buoyant and insoluble in water. Obviously, if you're in a kayak, you don't want the kayak to dissolve in the water, so it can float on the water with the kayakers. And here we have a couple of figures that are kind of redacted out, so I cut and pasted something from the Encyclopedia Britannica. So this is what they look like with their sort of long gangly branches. This is the monomer repeated over and over and over and over and over again, and this is kind of a ball and stick diagram showing what they look like. So the large ones are the carbons, and the small ones are the hydrogens that go with that. They would form a really, really huge sort of super molecule. So they say explain how the structure and bonding of LDPE results in a low density polymer that is suitable for use in kayaks. Okay, so for this one, you would need to say that they have strong covalent bonds, but not super strong. So they have the covalent bonds are strong enough to form waterproof layers. I guess that's what they're asking for. But the covalent bonds are the thing that keeps it together. So it's strong enough, and it's strong enough so that any polar force from the water will not be enough to dissolve it. It's just going to stay as it is. It's a fairly simple molecule. It's carbon and hydrogen. It has has very long chains, which make it quite light and also low density. So it has this sort of best of two worlds. So it has covalent bonds that are strong enough to not be dissolved by water, and long chains that are light and low density, so they have a lower density than the water. So they, well, not as dense as something else, that makes it a lot easier for it to float. So the not so strong covalent bonds give it a reasonably low melting point. So why is that important? Well, it makes it cheap. It's very cheap and easy to make. It's very easy to form into shapes. So you would just need to heat the plastic up, the LDPE up, put it in the form, and when it cools down, it's going to keep that shape. So it's going to be able to form, it forms easily into shapes when it's sort of semi-melted, but once it's set, it keeps that shape. So the large polymer structure forms a kind of a lattice layers. There are kind of sheets layered on top of each other that form a lattice that stays as it is. The other thing as well, it's really easy to repair as well. So it's really, really good. It is easy to break, and it does tend to bend a bit. So if you don't want it to bend a lot, maybe you look at some carbon fiber or something like that. But the covalent bonds are really why you'd want to have this. So this is me editing the video a little bit later on. I thought actually as well, it has low crystallinity, which means that there are gaps between polymer, between the actual monomers themselves. So that gives it the low density. Okay, so end of edit. Now we're told that the kayaker is looking for a new kayak made of stronger and harder carbon fiber sheets. So figure 3 shows 3 layers of carbon fiber sheets with a close-up of the atomic structure of the planes of carbon atoms that make up those layers. So this isn't the picture that's provided in the exam. It's one that I got, but it's carbon fiber is carbon fiber. So notice these hexagonal monomers that are sort of in a massive big sheet. These are carbon-carbon. There's the very, very, very strong carbon-carbon covalent bonds, and they're bonded interstructurally. So, is this covalent network, molecular substance, ionic material, or polymer, a metallic solid? Now, it's tempting to say that this is a polymer. It's not. It's a covalent network. This is a network of covalently bonded carbon-carbon atoms. So explain why the structure and bonding within the carbon sheet results in a kayak that is hard and strong. So there are very, very strong carbon-carbon bonds. And these are in a lattice. They're in a very thin layer layered on top of each other, on top of each other, on top of each other. And the carbon-carbon bonds are extremely strong. And the other thing is, as well as the layout of this means that it absorbs shocks. It distributes them throughout. It distributes shocks. So why is that important? It means that if you knock it, you won't put a hole in it. Okay. The other reason it's really, really good, it is far more rigid than the polymer that we had before. Downside, of course, is that they are way more expensive than polymers, and it's like a kayak like that would set you back several $1,000s. but you know that it's not going to break, and it's going to be really. So now we're asked, the shaft of a kayak paddle is made of aluminium, Al, or as our American cousins would say, aluminum. And there would be a picture of aluminium here, but I'm presuming you know what aluminium looks like. Select the type of material aluminium is. So hopefully no one got this one wrong. It's a solid metallic. It's definitely a metal. It's definitely not polymer. It's not ionic. It's not a covalent network either. It's not a molecular substance. It doesn't really form molecules. They're just really atoms of aluminium. So how does the structure and bonding of aluminium allow it to be malleable, forming long hollow tube of the shaft of the paddle? So what does malleable mean? Malleable means malleable means you can hammer it and shape it pretty easily. So why does it do that? It forms a lattice or a crystalline structure with a cation anion bond. Well, not bond, but link. So positive and negative ions link to each other in a crystalline lattice, and it is a layered lattice. So the reason that's important is that the layers can slide past each other, which means it's malleable. So the cation anion link, I'm maybe that's a bad word actually, attractive forces. Maybe better wording. What else is there? There is a free electron system. There is a sea of electrons. I've quite often heard it being described as a sea of electrons, which means that the electrons are free to move throughout between the atoms themselves. And that makes it very, very, very strong. It also means that if one part of it breaks, it's not going to rip through the rest of the material. If one thing is deformed, it's not going to sort of chip off or break away because of that sea of electrons. So figure 4 shows aluminium Al and the alloying of aluminium and magnesium Mg. I'm not going to include a picture here. You don't really need to know it. They ask you now to define the term alloy. Now, you can't just say for this, I don't think, just a mixture of metals, because it's not really. You have to sort of say something along the lines of it's a homogeneous mixture of materials, two or more, and at least one must be metal. So just saying it's two metals mixed together will not probably suffice in this case. You need to be able to say that it's homogeneous and there are at least two, at least one being a metal. So steel is technically, I guess, an alloy. It's really a mixture of iron and carbon. I think they treat it with some other stuff and mix it in. Bronze is an alloy. It's got copper in it. Alloys still technically metals, but they're homogeneous mixtures of metals, which means it's mixed sort of uniformly throughout. Okay, explain how adding magnesium Mg to aluminium changes the malleability of the material. So there is going to be a structural change whenever you have an alloy like that. The aluminium that we had before is uniform. It's anion, cation, etc. Okay. Adding magnesium, Mg, is going to disrupt that pattern. So it's going to be an irregular pattern, and it's going to distort this pattern. So why is that important? Well, it doesn't allow the layers to slide past each other, because now instead of anion cation, sometimes when they try to slide past each other, you're going to have anion, or cation with a cation, and it'll be like dogs and cats living together. It will be absolute chaos, and it's not going to slide past each other, and it's going to be resistant to deformation, which is a deformation. Deformation is a legal thing. Deformation, which means by definition it's going to be less malleable. This is a bit of a wordy one. You can pause it now and read the question. So table 1 shows the physical properties of aluminium and 2 different alloys that could be used for a kayak paddle. The shaft of a kayak paddle is formed with a long hollow tube, in case you didn't know what a paddle looks like. Float if it is dropped in water. It's always a good thing. If you drop it, you don't want it to sink to the bottom. Be hard enough to pull the blades through the water, so when you put the blade in, like Lisa Carrington, and sort of with incredible power thrust your kayak forward, it's not going to bend or break, and be light enough for the kayaker to lift and use. So as incredibly powerful as she is, she wants it as light as possible. She wants all of that power to go into the water, not in moving the kayak, the paddle itself. So let's compare these 3 things and see how they would suit. So pure aluminium, 2.7 grams per cubic centimeter. Aluminium and magnesium alloy, density a little less dense, which is interesting, 2.6 to 2.7, so that's good, which means it's more likely to float. Well, something that you make from it is more likely to float. Something floats if it has less density meaning the mass of the water that it would replace is less than the mass of the water. You get what less dense things are more easily floated. The steel, iron, and carbon alloy, like I alluded to before, its density is 7.75 centigrams per cubic centimeter, but it has a very high relative hardness. So, which one would be best? Well, let's look at them each one by one. Float if it is dropped in water. So this will win that. It's more likely to float a little bit more than pure aluminium. It is hard enough to pull the blades through the water, so that wins. But it really loses when it's light enough. So presuming that these things are the same dimensions, this will win. The relative hardness, we're going to say that this is how strong it is and how much little it's going to bend. So aluminium and magnesium alloy is kind of our winner, I guess, in that it wins 2 out of those 3, and one that really wants to win, this steel alloy. I mean, that's just unacceptably heavy. You wouldn't want to make a paddle out of aluminium. It would definitely not float, and it would be very difficult to go a long way, even if you were named Lisa Carrington. So this is me editing as well. I should also say that steel, because it's got iron in it, it will oxidize, meaning it will corrode and rust. So it's not very hardy in the long term either. Last question. Seawater is made up of H2O and salt, table salt, sodium chloride. Figure 5 shows the structure and bonding of the individual substances. So again, these are not the diagrams that were given in the exam, they're just ones that I've got for myself. This is water, of course, H2O, and we have here positive, negative, that positive and negative, and here we have this quite rigid structure of the sodium chloride. Sodium being positive, the chloride being negative. Okay, select the type of material that water is. Well, water is a molecular substance. They are discrete molecules. It is definitely not a metal. It is not ionic. It's not a polymer. It's not a repeated super molecule, and it's not a covalent network either. Sodium chloride. Let's have a look at it. Positive, negative, positive, negative. It's a lattice. It is not covalent. It is ionic in that case because it's polar bonds that bind them together, anions and cations that bind them together. Now we're asked about the white salt, sodium chloride. It's visibly left behind on the surface of the sea kayak. The salt is brittle and it crumbles easily when touched. So you should have that experience of knowing what large salt crystals that they kind of crack. Explain how the arrangement of particles in salt, sodium chloride, and the attractive forces between those particles leads to brittleness. Okay, so it's important to sort of note that sodium chloride is an ionic structure. So it has positively charged cations of sodium next to negatively charged anions of chloride. Chlorine. No, it'd be chloride, wouldn't it? It's chloride when it's mixed with something. It's chlorine when it's by itself. By the way, how can you tell that a cation is positive? Because cats have pores and cations positive. It's how I remember it, and that's my dad joke for the day. So it forms this lattice structure. When the structure is broken up, when it comes under stress, the layers move past each other slightly, and what that means is that you now have cation next to a cation and an anion next to an anion. They're not going to attract, they're going to want to repel each other. So now the ionic bonds are working against the structure of the structure at that layer discrepancy, and it's going to bust apart. That's why it's brittle. Yeah, I think that's pretty much all that you can really say about that. Apologies for the joke. So now we were asked to explain the properties and the attractive forces of water and the salt, and allow for the water to visibly remove the salt from the surface of the sea kayak. Well, one thing we need to know about water is it is quite a good solution. It is a really, really good solvent as well, meaning that you can dissociate these ionic things into them. So what happens is that if you look at the molecule for water, so we have our oxygen here and our two hydrogens here. This end here is going to be negative, and these two are going to be positive. So we have a polar molecule. What that means is that this is going to dissociate the sodium chloride. The sodium is, I think from memory, positive, and the chlorine is negative, and it's going to dissociate that molecule. So you're going to have the positive ends here surrounding the chlorine, and the negative ends there surrounding the sodium. So it's going to kind of split. The water is going to win, in other words. It's going to dissociate that sodium chloride, and that's going to overcome the lattice forces. So these ionic forces are going to be stronger than the lattice forces keeping it together, and it's going to do what's called hydrate, which means it's going to dissolve in water. Right, so a plastic bottle floats on seawater. The plastic bottle contains both air and fresh water. Table 2 shows the density of each of the materials. So here's the density of seawater. Seawater, because it's got the salt in it and other stuff dissolving into it, it's slightly denser than fresh water. Plastic bottle is also about 7 or 8% less dense than seawater, and that's a big problem. It means that plastic will float, and the air is a lot less dense than seawater. So really what they're saying is, why does the bottle float? So use the information in table 2 in your own knowledge of materials. Explain why the plastic bottle containing air and fresh water floats on seawater. Well, this relates to Archimedes' principle. The arrangement of particles isn't really relevant in this case. It's really density. So density is rho. It's the Greek rho. It's kind of a funky looking P. And what Archimedes' principle says. I can't even remember how you spell Archimedes. I think that's how you spell it. Principle. If I've spelt it wrong, don't make a comment. No one wants to hear. It says that an object in a fluid, and remember in physics, a fluid is a liquid or a gas, experiences an upward force, an upward buoyant force equal to the weight. I'm saying weight there, not mass, because I'm using gravity as well, of the fluid that it displaces. So what that means is that things that are less dense will float. Now, the fresh water, the plastic bottle, and the air are all less dense than the seawater. So each of these things individually will float. And in fact, there are examples of this. So fresh water will float above seawater. Now, if you go to a lot of the fjords down in Fiordland, there is a sort of a layer of fresh water at the top, and then underneath that is the layer of seawater. Plastic bottles, this is a big problem. When you throw a plastic bottle into the sea, it'll float and it will just congregate, and there are these, it's a growing and major ecological problem that plastic floats and it tends to group together and pollute the water, and you should know that a bubble in water will immediately float to the top. So all of these are less dense. So the density of the objects is less than the density of the water, or the seawater. So therefore there is a buoyant up force. So it's the weight because it's the mass times the force from gravity. So the water will sort of, all of these by themselves will float. So a combination of those must also float as well. It's a pretty easy question though, really. This is kind of the particles are really irrelevant in this case, because none of them will dissolve. We've already established that plastic doesn't dissolve. Air I guess air could dissolve, but air is contained in the bottle, and the fresh water is going to separate from the seawater. So all three of them would by themselves float. So all three of them combined will have a density way less than that of seawater. And this exam, it was a pretty easy exam. I've got to say, this question is pretty easy, and the one where it sort of asked you, is aluminium a metal? That's really easy. But that's the exam, and that's how I would answer those questions.